Now, probability is essentially, if we were to define probability, it is quantifying the chances of something happening, right? So essentially during rainy season, the chances of rain is higher, so the probability of rains during rainy season is higher than the probability of rains during dry season, right? So essentially when we are looking at chances, right, then we are actually talking about quantifying these chances, right? So the basic definition of probability, right, the mathematical definition of probability then becomes the possible outcomes, possible favorable outcomes divided by all possible outcomes. This this will quantify the probability of an event, right? So if let's say there are 3 in 5 chances that it will rain today, then the probability of it raining today is equal to 3 upon 5, right, which is equal to 0.6, right? Now you would notice some very basic things, that if let's say when I'm defining probability and when the denominator contains all possible outcomes, the possible favorable outcomes is going to be a subset of all possible outcomes, right? Therefore the numerator, in my definition of probability, the numerator is always going to be smaller than the denominator. Therefore the probability of an event will always be less than or equal to 1, right? And let's say if there are no favorable outcomes of the event, right, then the numerator will be 0. So the lowest possible number that the probability can take is 0, right? So the probability of any event is going to be always between 0 and 1. Now, with this basic definition of probability out of the way, now let's look at some other definitions and develop an understanding of what are some of the words which are used around around probability, right? So the first such definition is a random experiment. Now, a random experiment is essentially an operation which can produce a specific number of outcomes, right? But which outcome we do not know, right? So the example is throw of a dice, right? Now we know that when we throw a dice, the all possible outcomes, we can write them in a set which looks like this, right? So the throw of a dice is a random experiment which has possible outcomes 1, 2, 3, 4, 5, 6, but which one it will be, we don't know, right? So throw of a dice is a random experiment, right? And all possible outcomes 1, 2, 3, 4, 5, 6 is called the sample space of this experiment, right? So we've defined the second thing. So sample space is the set containing all possible outcomes of a random experiment. Now the throw of a dice, when this is an experiment, then the sample space is 1, 2, 3, 4, 5, 6, right? Then the next thing we will define is an event. Now an event is when we group some of these specific outcomes together, right, that becomes an event. For example, let's define an event such that event getting an odd number in the experiment throw of a dice, right? Now the event getting an odd number in the experiment throwing of a dice, so this event, if I call this event as let's say A, right, then A is going to have elements 1, 3 and 5, right? Because 1, 3 and 5 are the only odd numbers which are available in the sample space, right? So the event A, as I have defined it, has outcomes 1, 3 and 5, right? Now events can be of multiple types, right? Events can be elementary, like A previously defined is an elementary event, but compound events are basically combinations, are events which are formed out of combinations of experiments, right? For example, throwing of a dice twice, throwing of a dice 2 times and getting an odd number both times, right? This becomes a compound event. Okay, then um, some of the other event kinds can be looked at as follows, right? So let's define a certain event. Now a certain event is an event which will every time take place when the experiment is done, right? For example, let's define an event B, right, which is getting a number less than 8 in the experiment throw of a dice, right? So getting a number less than 8 in throw of a dice. Now we know that the sample space has 1, 2, 3, 4, 5, 6, right? And all the outcomes in the sample space, they qualify to be a part of B, right? Because all of them are less than 8. So actually B has 1, 2, 3, 4, 5 and 6, right? So all the possible outcomes in the sample space are also a part of B, which is an event defined getting a number less than 8, right? So every time the experiment is done, the dice is thrown, you get B, right? Therefore B is a certain event. Now interestingly, the number of elements in B, right, is always going to be, because B is a certain event, the number of elements in B is always going to be equal to the number of elements in the sample space, right? This means that the probability of B that we have defined, right, probability is defined as the favorable outcomes, right? So in this case, the favorable outcomes of B happening is 6. The sample space also has 6 elements, right? So for a certain event, the probability is always going to be equal to 1, right? Now, completely on the other side of the spectrum is an impossible event. Now, an impossible event is an event which will never occur, right? So let's define another event C, which says getting a number greater than 8 in the same experiment, throw of a dice, right? Now, C we'll look up the sample space and see how many outcomes match this event, right? So we notice that 1 not greater than 8, 2 not greater than 8 and so on until 6. None of the elements in the sample space are greater than 8, which means that C is a null set. Now if C is a null set, then the number of elements in C is going to be 0, right? Which means the probability of this event, of an impossible event, is going to be 0 upon the number of elements in the sample space, which is equal to 0, right? So completely opposite ends of spectrum, a certain event, the probability is 1, because every time the experiment is done, event B takes place. Impossible event, probability 0. Every time the experiment is done, you will never get the event C. None of the outcomes will match event C. Now let's define another couple of events for the experiment throw of a dice. So the experiment is throw of a dice, right? So the sample space is going to be 1, 2, 3, 4, 5, and 6, right? So let's define two events. Let's call event D as getting all the numbers greater than 4, right? So D will have 5 and 6, right? And let's define E as an event which has where the outcome is less than all the numbers less than 3, right? So E is going to be 1 and 2, right? So D has number of elements inside of D. The number of favorable outcomes in D are 2. Number of favorable outcomes of E are 2 also, right? So we can say that D and E are equally probable events. Now, why they are equally probable is because the number of favorable outcomes in D is equal to the number of favorable outcomes in E. So the probability of D, right, is going to be number of favorable outcomes 2 divided by number of elements in sample space, which is equal to the probability of E, which also has the number of favorable outcomes 2 divided by sample space 6, right? So both of these are equally likely events, equally probable events. All right, then let's start our discussion on exclusivity. Now look at these events again, D and E. Now you notice that D and E have nothing in common, right? So if you recall your set theory discussions, then D intersect E intersection D is a null set because they have nothing in common, right? You notice that 1 2 E, right? D has 5 6, nothing in common, so E intersection D is a null set, right? So if for two events there is absolutely nothing in common between them, then E and D are exclusive events, right? So there is absolutely nothing common means exclusive, right? So let's say if I were to draw a Venn diagram, right, of all possible outcomes of this experiment, throw of a dice, and if it has 1 2 3 4 5 6, all of these elements inside of this sample space, then this is this circle is the event E, right? And this circle is the event D, and notice that there is absolutely no overlap between D and E, therefore these are exclusive events. Now let's define exhaustive events. Now two events will be exhaustive if their unions are equal to the sample space, right? So if let's say we were to define define two events, let's use the next page. So let's say we have now let's say we have two events, G and H, right? G has the outcomes 1 2 3 and 4, right? And H favors the outcomes 3 4 5 and 6, right? So we will call G and H if their union is equal to 1 2 3 4 5 6, right? 6. We know that the sample space also has 1 2 3 4 5 and 6, right? So if the union of two sets is equal to the sample space, then G and H are exhaustive events, right? The whole idea is that they are exhausting, G and H together are exhausting all possibilities in the sample space, therefore G and H are exhaustive events, right? So now we know exclusive and now we know exhaustive. What if two sets are exclusive and exhaustive? Right, so if two events are both exclusive and exhaustive, let's define these events. Let's define event I and J such that I has elements 1 and 3 and J has elements 2 4, 5 and 6, right? So this is all again for the experiment throw of a dice. Throw of dice. Right? Now in this case, notice that I intersection j is a null set. They have nothing in common, right? And I union j is actually equal to the sample space, right? They combine together to complete the sample space, right? So if both of these conditions are satisfied by two events, right, then event I and event j are exclusive and exhaustive. In other words, I and j are complementary events. Now the whole thing about complementary events is that I completes j, right, in giving us the sample space. J completes I in giving us the sample space, right? This means that I complement is equal to j, right? And j complement is equal to I, right? Now the important thing about complementary events is that if we know the outcomes, the favorable outcomes of one of these sets, then its complement will have all the remaining outcomes within it, right? So you subtract this from the sample space, right? So if we subtract I from the sample space, we get j, right? And if we subtract j from the sample space, we get I. So this is an important property of complementary events. Now what this also means is that the probability of I, right, plus the probability of j is equal to the probability of sample space, right? In other words, probability of I plus probability of j is actually equal to 1, right? Which means that look at this. So if I has two favorable outcomes, right, out of 6, then the probability of I is 2 by 6, right? Now j has the remaining 4 outcomes, so the probability of j is 4 by 6. Now you add these two, their sum is equal to 1, which is the probability of the sample space occurring, right? So this is how we look at both exclusivity and exhaustivity.